Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. In episode 15 of the Network Plus Prepcast, we turn our attention to virtual local area networks, more commonly known as VLANs. These logical groupings are a foundational tool for organizing traffic, enhancing security, and optimizing network performance. Unlike physical segmentation, which relies on separate hardware or cabling, VLANs allow you to segment devices on a switch based on their function, role, or department, all without moving a single wire. This flexibility makes VLANs a core component of modern enterprise network design. Understanding VLANs is essential because they are used everywhere in corporate environments. Organizations use VLANs to divide their networks into smaller, manageable sections that correspond to business functions like voice traffic, administrative systems, or guest wireless access. Segmenting the network this way reduces broadcast domains, improves security boundaries, and simplifies policy enforcement. VLANs are particularly useful in settings where devices are physically spread out but still need to be treated as part of the same logical group. This makes them powerful, scalable, and efficient. A VLAN is a logical network that operates at layer 2 of the OSI model. It allows you to group switch ports together as if they were on the same local area network, even if they are physically located in different parts of a building or campus. Devices within the same VLAN can communicate directly, just like they would on a traditional broadcast domain. Traffic from one VLAN is isolated from others unless routing is explicitly configured. This makes VLANs ideal for separating functions such as user workstations, IP phones, and printers within the same infrastructure. VLAN tagging is what allows traffic from multiple VLANs to coexist across shared links. The most commonly used standard for VLAN tagging is IEEE 82.1q. This protocol inserts a small tag into the Ethernet frame header that identifies the VLAN number the packet belongs to. Switches use this tag to ensure the packet remains within its assigned VLAN as it crosses trunk links. Trunks are essential when connecting switches or routers that need to support multiple VLANs over a single physical link. Two concepts often mentioned in the context of VLANs are the default VLAN and the native VLAN. VLAN 1 is typically the default VLAN on most switches. It includes all ports until they are reassigned. While it functions like any other VLAN, it's generally considered best practice not to use it for user traffic. The native VLAN is the one used for untagged traffic on a trunk port. Trains belonging to the native VLAN are transmitted without a tag. Both concepts play a critical role in managing how traffic flows across and between switches. When discussing VLANs, it's important to differentiate between data VLANs and voice VLANs. A data VLAN is used for standard workstation traffic, things like file transfers, email, and web browsing. A voice VLAN is a specially designated VLAN for IP telephony devices. This separation allows voice traffic to be tagged for quality of service and prioritized over data traffic. Many switches support the configuration of both a voice and data VLAN on the same port, allowing an IP phone and a workstation to share a connection without mixing traffic. Static VLAN assignment is the most common method for associating switch ports with a particular VLAN. In this setup, each port is manually configured to belong to a specific VLAN. This is simple and effective, especially in smaller networks where devices do not move around frequently. However, it can become tedious in larger environments or in situations where users regularly switch desks. Because of its fixed nature, static assignment requires careful documentation to prevent confusion and configuration errors. Dynamic VLAN assignment offers a more flexible alternative. It uses authentication services like Radius in combination with MAC address or user credentials to assign the appropriate VLAN to a device when it connects. This allows the same port to serve different users at different times without reconfiguration. It also simplifies moves, adds, and changes across the network. When a user logs into a new device or location, the network assigns the correct VLAN based on identity, ensuring consistency and security across the infrastructure. VLAN trunking enables multiple VLANs to be carried over a single physical connection between switches or between a switch and a router. This is especially useful in multi-floor or campus networks, where you don't want to dedicate a cable for every VLAN. On a trunk link, each frame is tagged with its VLAN ID using 802.1q, and the receiving switch uses this tag to forward the packet appropriately. This setup allows you to maintain consistent VLAN definitions across multiple switches, simplifying centralized management. A key benefit of VLANs is their ability to contain broadcast traffic. Each VLAN acts as its own broadcast domain, meaning that broadcast messages like ARP requests or DHCP discovery packets are limited to that VLAN. This reduces unnecessary traffic across the network and improves overall performance. In large networks, containing broadcast traffic is essential to maintaining scalability and ensuring that devices only see relevant communication. Without this containment, broadcast storms could quickly overwhelm the network infrastructure. Configuring VLANs begins with creating the VLAN on the switch. This includes assigning it a VLAN number and optionally a name for clarity. Then, switch ports must be assigned to the correct VLANs, either as access ports for a single VLAN or as trunk ports for multiple VLANs. Verification is typically done using show commands that display port assignments, active VLANs, and trunk link status. These tools help ensure that VLANs are properly set up and operating as intended. For more cyber content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. VLANs offer numerous benefits in network design. First, they allow administrators to logically group devices based on function rather than location. This means all printers, or all administrative systems, can reside in the same broadcast domain, regardless of where they are physically located. Second, VLANs enable role-based access control, where users in different departments receive different levels of access based on their VLAN membership. Finally, they simplify segmentation, making it easier to enforce security and performance policies without the need for separate physical infrastructure. When devices in separate VLANs need to communicate, routing must be introduced. This is known as inter-VLAN routing and typically requires a Layer 3 device, such as a router or Layer 3 switch. The most efficient method is to use switch virtual interfaces, or SVIs. Each SVI represents a virtual router interface assigned to a specific VLAN. Traffic between VLANs is then routed internally by the switch. This method is faster than using an external router and is standard practice in most enterprise networks with multiple VLANs. VLANs also interact directly with quality of service mechanisms. By assigning voice traffic to a dedicated voice VLAN, switches can apply special priority tags that give voice packets preferential treatment over standard data traffic. This prioritization helps ensure smooth voice and video performance. Additionally, traffic classes can be defined by VLAN, allowing policies to be applied at a group level. For instance, a department requiring higher bandwidth can be placed in a specific VLAN with enhanced service guarantees, while lower priority traffic can be isolated in a different segment. Security is another critical consideration when implementing VLANs. While VLANs provide isolation, misconfiguration can create vulnerabilities. One such risk is VLAN hopping, where a malicious device tricks the switch into forwarding traffic to another VLAN. To mitigate this, administrators should disable used ports, avoid using the default VLAN for user traffic, and explicitly define allowed VLANs on trunk ports. Restricting access between VLANs using firewalls or access control lists adds an additional layer of protection. In wireless networks, VLANs are just as important as in wired environments. Wireless controllers and access points can map each SSID to a specific VLAN, ensuring that guest users, voice devices, and corporate clients are isolated from each other. This separation prevents unauthorized access and allows policies to be enforced based on user type. For example, a guest SSID might provide internet access only, while the voice SSID ensures low latency service for mobile phones. This mapping helps maintain the same logical segmentation in wireless that exists on the wired side. Troubleshooting VLAN configurations requires attention to detail. One common issue is incorrect port membership, where a device is placed into the wrong VLAN, causing loss of communication. Another frequent issue is trunk port mismatch, where the sending switch and receiving switch disagree on which VLANs are allowed over the link. If a VLAN is not present on a trunk link, devices in that VLAN on opposite sides will be unable to communicate. Diagnosing these problems often involves verifying port settings, trunk configurations, and ensuring that all VLANs are consistently defined across switches. In large networks, VLAN design must be standardized to maintain consistency and simplify management. This includes using consistent VLAN numbering schemes across all switches. For instance, assigning VLAN 10 to voice traffic and VLAN 20 to data traffic throughout the network. Centralized management tools or configuration templates can automate the deployment of VLANs and ensure uniform policy application. Documentation is also critical. Keeping clear records of VLAN assignments, port mappings, and associated policies helps prevent misconfigurations and simplifies troubleshooting efforts over time. Ultimately, VLANs are a powerful tool for network segmentation and traffic control. They support cleaner network architecture by separating traffic types, enhancing performance by reducing broadcast traffic, and improving security by isolating sensitive systems. Their flexibility allows organizations to adapt their networks quickly to changing needs, whether adding new departments, deploying new services, or implementing stricter security policy. VLANs are foundational to scalable, efficient, and secure modern network designs and are used in everything from small office setups to large enterprise data centers. To recap, VLANs provide logical segmentation at layer 2, offering a flexible and powerful way to organize and control traffic. They reduce broadcast domains, support security through isolation, and enable quality of service for time-sensitive applications like voice and video. Whether implemented statically or dynamically, VLANs form the basis for scalable and manageable network designs. Mastering VLANs is key to building, troubleshooting, and securing enterprise networks and is a critical concept covered on the Network Plus certification exam. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.